Twente, Netherlands. The first speaker is a keynote presentation. The Professor Louise Olsson from the Chalmers University of Technology, Sweden, will give us the NOx adsorber CO influence of passive NOx adsorber over the palladium emitter. Yeah, please welcome Professor Louise Olsson.
Thank you very much for the introduction. Also, thank you very much for inviting me here to give a keynote lecture regarding passive NOx adsorbers. So this one is collaboration between Sweden together with ABL in Austria. I would like to introduce the other courses. We have Dave now and Chris from Chalmers, and also is a class from ABL. And today I will talk about passive adsorbers and focusing on the effect of CO as well as SO2. So first of all, clean emission from vehicles. So we have the source gas from vehicles, we have CO, hydrocarbons, nitrogen oxides in the emissions, and NOx. It's increasing acidification, increases smoke formation, it's toxic and so on, so it's very important to remove the NOx. Today, NOx can be efficiently removed by using selective catalytic reduction of ammonia. However, reducing the urea and dose at low temperature, so you need about 200 degrees to dose the ammonia, dose the urea. Otherwise, it will deposits such as beerite and so on. So it's actually an issue to remove nitrogen oxides during cold starts, and therefore have this constant start to develop passive NOx adsorbers. So the DNA principles is to have nitrogen oxides linear. You first put a passive NOx adsorber that absorbs the NOx at low temperature, and when the temperature source gets higher, the NOx in here will be released. And then you can dose urea and it will be converted over the zero catalyst. So then the DNA principle is to store the NOx at low temperature and then release it about 200 degrees where the SR catalyst is active. So the objectives of this work is to develop a DNA chemical model to describe the post-term period under different gas conditions. We will look into the effect of low CO concentration versus the NOx storage. However, when you have higher CO concentrations in the literature, that it deactivates the passive NOx adsorbers, but also developed that based on experience together with modeling. We have also included the effect of sulfur, and finally we are looking into how we synthesize cell 13 in different ways to increase stability. So the outline of this work will in general about we continue to describe a basic chemical model for DNA, where we have NO, oxygen, and water in the feed. Next step, we include low CO concentration as well as high CO concentration in the deactivation modes. And then I will continue over to the effect of preparation procedure of the flame cell 13 to enhance CO resistance, and finally talk about the kinetic model for acid posting. So here's the scheme. So first, start with synthesizing adsorber using cell 13 in claim on it, and then we go on. We use various optimization techniques to understand the mechanism, and then we do use program experiments to do NOx temperature program adsorption experiments. And finally, we kinetic model using ABL. And we do both kinetic modeling on data level as well as on system level. So first, we have a basic kinetic model where we have between 200 to 400 ppm NOx, mainly NO. Work for 8 so it's a multiple cycle test. Then we continue over at between 200 to 400 ppm CO. And then we continue over again to the CO degradation with 4000 ppm CO. We verify, so go along, develop the model, always go back to make sure that the model also can describe the conditions. And then we develop a poisoning model, where we put in 1320 ppm as and finally we verify that the total model can describe all the different aspects of the exam. So release the genetic model. So here, first, it will really good enough. So more than 750 degrees. It has been found earlier, this is very important to degree healing samples because that would distribute the blame of the field. Then we decide if it's shown here. So if you look at the magnification here, this is a heat capture program absorption for 50 experiments. And at 80 degrees, where we add 2 ppm henna together with 8% oxygen of fats. And then we increase the temperature in the same test atmosphere. And then we have graduation, and then we cool down. And we do this multiple times with different NO concentrations. As you can see, first with 200, 300, 400. So here are the results. So the top panel here shows the NO and NO2 concentration. When the NO concentration is the solid line and the NO2 is the dashed line versus the temperature. You also see the temperature here. Facing, then one panel shows the top NOx. So first, if we integrate the absorption process, you can see that the NOx to plane ratio is 1:165. So they are quite similar, showing that plane cells are saturated. It should also be like a quite high dispersion, since we have the maximum you can get would be 1 on the plane ratio. And now you can see that when increasing the temperature, you can see here that we have consumption here and energy production to 66 degrees. We see at 252 as well as 371 degrees, we have absorption peak. So this would suggest that we have 3 different sites which was used in the model. And for both of the reasons that the NO2 here, one of the reasons here is that NO was partially oxidated from NO2 when it reduced later. So we also examined what happens reducibility. So this is a part of cycles, 72 and 77 in the end. And we can see that the NOx is the same for cycles, showing that there will no degradation on the catalyst. In this condition, as I said, because here we do not have any CO. So with only NO and oxygen, it's reproducible. So we see no degradation. We did address the spectroscopy. And we can see here we got a peak around 1450 here that then suggested we have nitrates, and that also that's occurring on the peptide side non-particles that formulate nitrates. So that the mechanism of the sites we have used 3 sites, as I mentioned before. So, and those 3 sites is well known. The copper zeolite working with CR, that copper, and it's the same way with lead, it can shift bind to aluminum like this. Or it can shift bind to 1 aluminum and then charge balance with OH. So we have 2 different types of ion exchange sites. The second PD OH, the second PD set. And then we also have radium oxide clusters. With this, we developed models. And we have the reactions on the 70 set. The reaction where we have radium on 1 aluminum charge balance with OH group. And also where we got nitrates on the radium oxide clusters. And then we will go global reactions that for N-oxidation. So here we can then see the results. This is first the experimental sequence. So you can see that we have 200, 300, and 400 ppm NOx. And the results here, we have 2. So the red curve is the NO, and the blue curve is the N2. The solid line is experiment, and the dashed line is simulation. And that's the concentration. So this is the 200 ppm now. So this is the absorption, and this is where we're ramping, and we are ramping in the presence of NO, as you can see here. And this is using 300 ppm or 400 ppm NO in the input. So this is now our basic genetic model to describe the passive NOx adsorber. And based on that, we will continue over to make additions to it. And first, we will add low CO concentrations. So in this one here, we add 200 ppm of CO, or 400 ppm of CO, and we have 200 ppm NO and 8% oxygen and 5% water. So you can see the experimental results changing the CO concentration. So that on here, we have the NO and hydrogen concentration, and we have the NOx concentration. If we then look into the NO to plane ratio, we can see that it was from 0.64 to 0.6869. So it's slightly increasing. That suggests the CO is slightly increasing storage amounts. We also see that the energy peak here, when we add CO, it vanishes. We suggest the reason for this is that the expansion reacting with energy from the energy, but now we need to see what we can produce CO2 so that can explain this part. And then the fun point here, so that 200 degrees is marked here, the red dash line here, so most of the NOx is for about 200. So when you examine, you start to towards level 5, it's very dense. Or I can see that the NOx is reduced. Yeah, so as long as we have no CO filtration, we don't see any of this degradation. Then we will understand what is the role of CO, discussed in literature. So we look at the CO and CO2 profiles. So this is CO plus CO2. And we can see here a small distortion here. But however, if we integrate this, it only corresponds to CO plus CO2 per palladium 0.06. So it can only explain like 6% of the palladium covered with CO. So on our catalyst, it's not likely that the main reason for the effect of CO is that CO is absorbed on it, since we have split the absorption. With that example with XPS, without CO, treat the catalyst and then take the air to the XPS chamber. So this is the treated without CO after the cycle to 200 ppm CO and after the cycle to 400 ppm CO. So if we look here on the evolution, the blue here is palladium metallic. So if we don't have any CO, we don't see any metallic palladium. And when we are increasing the CO to 200 as well as 400 ppm, we are seeing an increased amount of metallic palladium. So it's up to almost 60% palladium metallic. And in the same way, the oxidized plate species decreases. So we suggest that in the modeling that the main reason then for the enhancement of change activity with CO emission is due to that changing the oxidation state. So then we add in action steps this. Reduce the set of the set by CO and also the palladium that's charged and always reduced. And we have also reduced the palladium oxide particles. And then we can see the result here, where it's we model these 4 cycles in row. You can see the results here. So this is NO, the red, blue is again N2, solid ion experiment, and dashed line is the model. So, and this is equal to 200 ppm CO as well as 400 ppm CO. So you can see it's quite a large difference in absorption behavior with 200 ppm CO compared with 400. So there's a quite large difference. So this was now an example of modeling when you see low CO concentrations. But then it's well known that if you have high CO levels, you will deactivate the catalyst. And we want to include that in our modeling. So here you see blend cycling. First we have two cycles, 200 ppm NOx, 8% oxygen, 5% water as our base case. And then we add 4,000 ppm CO, that's the red piece here, less than the protocol. So we do 13 cycles, 4,000 ppm CO, present with adsorption and desorption. And here are the results. So this is the NOx concentration. Here. The first panel shows the first cycles. So cycle 1 is the black. So here. And then the second cycle is repeated. So the first cycle is the first volume high CO level. That's the blue. So you can see a very large effect here for the black and blue, just the first time sees this high CO situation. And then it continues to deactivate. Here we have cycles 7 to 15. So what you can see is that at some point it has deactivated becoming severe and then it stopped deactivating. But it's not much stopped at that point. So we are seeing also these people also shifted to a lower temperature, so that we suggest that we have change in flame site. And we can also see that first the depth becomes slower and then it goes on. And this is something we don't like include in modeling. Here is the integrated values of NOx amount first cycles. We did have two first cycles which without high CO level, and then we start at 4,000 ppm. So what we can see is that first, and then and we then used the mental centering equation to find more about the centering equation, these references here. So we use the same type of mental centering equation as was done in those papers and applied it to the passive NOx adsorber. And what we see here is that the n in this equation here were split into two first, which would suggest also ripening, should be 1 and 4. And then we have the n equals 6 in the later part, which is particle migration. So based on these, we implement an model first that we are for ripening, followed by a particle migration to explain the deactivation. Then of course we need to characterize this as well. So here we have 10 thoughts. The first one is after 400 ppm CO, and the second one image visual effect after cycle 4,000 ppm CO. And as you can see, we still have a lot of small particles left when we're done 400 ppm CO, but when we use 4,000 ppm CO, they are huge particles, so we've shown that we have had a large sintering with this high CO level. And then we look to 1.13. We could also see, look into this peak here, that flame oxide fraction also increased after variation. So these results then are showing that flame is centered on high concentration of CO. Then we examine the drift. This is 200 ppm NOx, 4,000 ppm CO, 1% water, 8% oxygen at 8 degrees. And this is spectrum from 0 up to 24 minutes. So what we can see is that after a while, see here, that 2144, which corresponds to palladium with CO layers on it, are increasing. So we don't have any initially, but when it goes for a long time, we do see that it's growing. So with this, we can see that with high CO levels, we get characteristics palladium COX. And from literature, this paper here has been shown earlier with cell images that there is a palladium movement already at room temperature if you have CO ligands bind to palladium. So the results from that paper are supporting our results where we are seeing very high CO levels in combination with centering. So palladium CO in those palladium formed, they then suggest this activated ripening and form palladium oxide particles. And these particle were not stable enough, so that it would undergo particle migration forward. So then we have this two-reaction mechanism. We form the plate and carbonites. The reaction step for possible ripening to form plate nanoparticles. And then we need to add an anode and CO onto these plate nanoparticles. And that can explain that we have different strengths, that the shorter deeper shifted. And then we need to add also the ripening. We experimentally saw that there was first a fast deactivation and then a slower one. So after that possible ripening, we had the particle maturation, we had a reaction. And we had a reaction step. As well as see this. So then we can see the results here of being CO deactivation. Again, that is Anna, we was N2, Scully Daniels experiment, dash minus the volume, times 3, and here's the temperature. So this is the first time where we don't have any high scale concentration, and the third cycle is the first time. CO is the large difference here. That is cycle 4, where we see a very large deactivation. And what was level 5, and then it level stop, cycle 750. So now we have developed that model for the high CO concentration. And then we'll continue to look at the synthesis method. So what I've shown up to now has been that we first start from step 13. In the plate nitrate, if the plate is set, we try 80 and it was 95. What we now did was to stop at ammonia as step 13, so we didn't design for the hydrogen form. Instead, we introduced ammonia as I said, plate nitrate. And then we did two different ways to dry it. One was freeze dry. And the other one dried at 80, and after that, the sun. So if we then look into the results from this, we will cycling 2 cycles without CL and then 5 cycles before after PPM CO. So same as before, but now we 5 cycles with high CO level 13, since it had level after cycle 5. And if we look here on the stored NOx, then we have high CO level, see the deactivation. But interestingly, see that the freeze dries down on the better part. Therefore, very little in the first cycle, so 3% compared to 30%, and it kept on stable. It still deactivates, but it deactivates slow. And then here, we come CO, and we can see that we gain some activity, but not at the beginning. But also after these high CO levels, the dimension was 46% for the freeze dry sample and 66% for the 80% dry sample. So when we look into the TM connects, we can see that the freeze dry use, we go from 1.4 up to 12 nanometer on average. The 8-degree sample had bigger particles at the beginning. We got 2.9 nanometer on average, and we got 17.7. So here you can see that the freeze dry has smaller particles both initially as well as after it has been used in the cycle. If you look into the next study, we can also see an effect. So we go to the cycle. Stay with what's reduced. So then we used the model we developed and changed the number of sites we had in the preparation. And then we described these dry samples. So we have 8 degrees dry samples. So this is cycle 3, 5, 8, the freeze dry, and 8 dry samples, 8. 3, 7, 3, 5, 8. So, and then continue over to the acid poisoning. So then we develop acid poisoning. In this case, we have the base shown here before. Then we have the ammonia cell 13, but now we compare the room dry sample and compare it with the age dry sample. And we use this for acid poisoning. We have the inlet gas concentration versus time on stream. And this is many sites. Here we have two sites. Then first, where we have ppm NOx. Good. And we see we have the NOx. And then after the two cycles, we start to add SO2, different levels of SO2, between 25 and 100 ppm. About there, and we will add SO2 to the absorption desorption step here for all the cycles, and then there's cycle 8 and 9 after. So then to look at the results. Here we have the NOx in concentration versus time on a group dry sample. So the first thing we can see is that the decarbon 290, which we decide to end up on latent sites that are binding to the liquid sites. And we can see that it disappeared after acid poisoning, suggesting that these sites were vulnerable to acid. And what we see is that the HFC sample have much more of these sites. So the threshold, which is the red one, so showing that the room dry sample contain less 7%, which would not be good since it is very vulnerable to acid. And then another thing we can see, we have added 2 years per 12 months before. And in these experiments, so far, there's no CO. So we can see as we CO, so that we have the CO, which will tend to disappear, and that also happens with SO2. We could also see that this N2 is removed, so suggesting that the plate nitrate and those reactions take oxidized sites are suppressed by sun. So interestingly and very surprisingly, we see that if we compare the red for SO2 with the blue one, this is the SO2, it's much higher. So we are storing more NOx during sulfur in the sample, which we were very surprised about. And we see some of the effect here also on the 80 sample. So if we then look into the dissolved amount, here we have room dry sample with different SO2 levels. First, these two have no SO2, and then we have 26 ppm, 52, and 104 ppm just in one. So we can see that the total amount of NOx dissolved is increasing when we have SO2. However, when we turn off SO2, it goes back, and it actually goes back lower than it was before. So during the SO2, it is actually enhancing it, but then after we turn SO2 off, it goes back to a lower deactivated state, but not so much lower. We can see here, we have in this figure here, have 80 degrees, which is the black, then prepared by trying to 80 degrees and comparing it to the room temperature for a long time. So we could see that this induced effect, that we get more storage of NOx when we have SO2 is much higher than room driving. So it's really depending on latent sites. I think this is something that's very characteristic for the plate SSL 13. They're extremely sensitive to how to prepare them. And what kind of plate species you have, both for how they interact with NOx, CO, as well as SOx. So it's very important to think about exactly how to prepare them depending on the functionality you want to have. And we can see here that after sulfur, that the room dry sample had 10% degradation compared to the initial, but it was 26 with 80%. So SO2 enhances with DNA performance. Also, the employees and room dry sandwich was more consistent. So then the characterization, if we look here into fraction here of palladium 101, we can see that the fraction increased after poisoning. And if we look into TM, we can see that the room dry before and after poisoning went with from 3 to 7 nanometers, so they increased. So SO2 also reduces agglomeration of the palladium sites, but not as much of all as I've seen them. So then using drift, we see that the cell piece here strongly influenced it's level lower intensity for both. So also the drift that exists at the 70% are the one that's most vulnerable to the estrogen. And then we developed a model with Olsson said S2, but we add the NOx adsorption on the 7-POH to explain that we have this higher NOx release. And we did that for both on both sides. And then here you can see the results. This is a room dry cycle 2, which is done before S2. Red again is experiment, the solid line brings the N, which includes N2. The solid line is experiment, and the dash line is body. This is cycle 2, room dry, and this is 80 degrees room dry. So you see that it is quite different aspects. And then cycle 3 with sulfur, cycle 7, and 8 are also. So then to come to the conclusions. So we have developed a passive adsorber for kinetic and used 3 different sites to describe it. 2 ion chain sites where palladium is either binding to aluminums or palladium binds to one aluminum charge balance to OH. And the third site is palladium oxide clusters. You can see that palladium, I describe palladium when, and we first develop the model without the addition of CO, and then the below CO concentration that influences the stability as well as the amount of stored. Then we model the effect of high CO levels and the activation mechanism, and then the acid chemistry. The anthropoid of CO was illustrated. We have low concentration of CO. Reduced to palladium 2 species, palladium 1, palladium 0, which is called XPS. And we suggest that this increases the NOx binding strength. And then when we have high CO levels, we form these palladium CO compounds that are increasing the ability of the platinum. And then first we have binding, which is then followed by and then roll up SO2. So we have the ion-shaped palladium sites, and we saw that the one that has the palladium to one aluminum charge balance OH group is more stable towards SO2 poisoning. And we also saw that SO2 then leads the NOx storage, so we get more NOx storage during the addition of SO2. However, when we remove the SO2, the sample is deactivated. And then we finally developed a passive adsorber that had a higher tolerance towards both SO2 as well as high CO levels. And that was depending on how we did the driving of the sample after introducing palladium. And then I want to come to the technology. This work has been a collaboration between chemical engineering and Chalmers University. Chalmers University together in India. Austria, so launched this collaboration, also wanted to launch the founding union, and also I would like to thank the organizers who invited me to present my work here. Thank you for this.
20, Netherlands.